Hello. Today we are doing the round pipe flow example, and for that we need the Navier-stokes equations in cylindrical coordinates as we spoke the other day, and you'll find those in Appendix D. So let's look at those closely. We are familiar with the Navier-stokes equations in Cartesian coordinates, the x, y, and z. And the relationship between the Cartesian x, y, and z and the polar coordinates r, z, and theta is as so: the sine cosine for the r, theta, x, y, and the z is z. So your continuity from Appendix D comes out to be the velocity component in the r direction is Vr, V theta is in the theta direction, that's the tangential velocity, radial velocity, and the Vz is the axial velocity. So axial velocity, Vz, V theta is the tangential velocity, and Vr is the radial velocity in the pipe. And r, theta, and z are our independent variables, which are our coordinate system. So the r, z, and theta momentum conservation equations come to be as so, and here they're written in vector shorthand notation. You have the Laplacian over here, and you have the convective derivative, or the derivative moving with the fluid element, and here the r momentum. So we're operating on the r velocity, Vr, and Vr. These V thetas come because of the coordinate transformation from radial to from Cartesian to polar. So that is your r momentum equation, and the v dot del operator is so. And if you have it operate on Vr, so you plug in Vr, and this would be, so this whole term is actually all those 1, 2, 3 terms. And same thing for the Laplacian operator. That's the Laplacian operator. So if it operates on something, and that something in our case is the Vr, so you plug Vr and you get so. So that's the r momentum, theta momentum in a similar fashion. That's what it looks like. But we're primarily interested in the z momentum equation when we're dealing with the pipe flow, so we'll come to it in a second. But this is the z momentum equation, and you can see it looks very similar to the Cartesian coordinate, except we have some theta. So you have the dr, d by dr, d by d theta, and d by dz. And here you have the 1 over r 1 over r squared d del squared d theta. So, but in this format, it looks the same as it is in Cartesian coordinates. Okay, so let's look at our pipe. So consider a pipe of diameter d, or radius r, and the pipe has a length L, and you supply some high pressure at the inlet of the pipe and some low pressure at the outlet of the pipe, and we're making the assumption that our pressure drops linearly with L or Z. So let's look at our coordinate system. Z is the axial along the length of the pipe. R is in the radial direction, so it's from the center of the pipe towards the wall of the pipe, and theta is the tangential direction. So this is a pressure-driven flow, and as we said, we're assuming a constant pressure, a linear pressure variation with Z, with the length of the pipe. So L is along the length of the pipe. So dP dZ will be just P plus minus P minus, because it's linear, P plus, so at the inlet, minus the P minus divided by X at the inlet is 0 minus L. So you see, because this thing is positive, and this thing is negative, this whole thing is positive, and you have a minus L. So the pressure gradient is, for you to have the flow going from left to right, you want to have your pressure gradient to be negative. And it's a negative that is a constant. We're making the assumption. So what are we doing here? What we want is, we want to analyze this pipe flow. We want to know what is the velocity profile, how does it look like in this pipe, and we want to know things like, if I supply this pressure and I supply this pressure and I give you the radius of the pipe and the length of the pipe and the type of the fluid, how much mass flow rate is going to go through it. And if I want to know how much mass flow rate is going to go through this pipe, I really need to evaluate what is the velocity distribution as a function of R, right? So this could be a velocity distribution. We'll see what it looks like as we analyze our flow. So to make the solution of our Navier-Stokes equation simple, we're making the assumption that the flow is unidirectional in Z. So we only have Vz, there is no tangential velocity, there is no radial velocity, so Vr, V theta, or Z. And that in its own merits is another manifestation of saying that the flow is fully developed. We're being fully developed in the Z direction, d by dz of the flow velocity is 0. We're making the assumption that the flow is axisymmetric and that we're ignoring gravity. So here are the assumptions. We have seen them before. So when we're saying that our flow is 2D, that means 2D in R and Z. That means it's independent of the third dimension, which is theta. So d by d theta is 0, which is also the same thing as being axisymmetric. So 2D and axisymmetric, because axisymmetric tells you d by d theta axisymmetric tells you that d by d theta is 0. So here I should type axisymmetric. The flow is steady, so we're dealing with a time equal infinity after we started the flow. So here you're probably blowing with you get a straw, you're blowing and it's on one end, so you're applying high pressure with your mouth, and you're open to the atmosphere on the other end of the straw. So this would be one example of what we're doing here. Flow is unidirectional, and by unidirectional we mean it's only the velocity, the only velocity that has a value that is non-zero is in the Z direction. So the velocity in the radial direction and the theta direction are 0, and we're supplying a constant pressure gradient. So we want to know what is the velocity distribution Vz as a function of R. So this is R and this is Vz. What is the shape of this profile? Let's work on that. So we want to do this using the Navier-Stokes equation. So this is our continuity, and let's go term by term. I have Vr, and Vr, as we said, is 0. I have V theta, no tangential velocity. So we end up with d by dz of the velocity to be 0, which is also saying that our flow is fully developed. So that's how we see that our unidirectional flow and being fully developed deliver the same message. So all three terms are identically 0. Now let's look at the R theta and Z momentum equations. This is the R momentum equation, so every term cancels out, or we can end up with dPdR 0, so the pressure isn't independent of R as long as you don't have gravity. Same thing here, the pressure would be independent of theta because every other term has a VR in it or V theta, so it cancels out, and same story. Now with and this is expected that the R and theta momentum will boil down to pressure terms that are constant, primarily because our momentum is in the Z direction. So we'd expect that the equation that would have non-zero terms on both sides would be the the Z direction momentum equation. So let's look at the terms in there. that's the steady term, so it's 0. And here we have our convective velocity. So if you spell this out, you'll find out that it's identically equal to 0. And anytime you have a fully developed flow that is unidirectional, the convective derivative will actually be identically equal to 0. And this is the harder part of the equation to solve because it's nonlinear. And then we're ignoring gravity, so we end up with pressure. We say we know that we have a pressure because it's in the givens, dp dz is constant, and we end up with the Laplacian, the viscous stresses. The nu is mu viscosity, dynamic viscosity mu over density rho. Okay, so let's look at this boiled down Z momentum equation. So we have the pressure on one side and the viscous stresses on the other side. So let's now expand this Laplacian. And as I said previously, the nu is the kinematic viscosity. It's equal to the dynamic viscosity over density. What are the units of kinematic viscosity? It's meter square per second. So it's like an area velocity. You throw a stone in a pool, you see those concentric circles going out. This is one example of looking at area velocity. Dynamic velocity has units of Pascal second. So you want to be able to go back and forth between dynamic and kinematic viscosities through the density rho. So let's spell this out, the Laplacian, and plug in Vz. So let's see. Let's look at the terms. If we look at the del square Vz by dz square, that's fully developed flow, so that would be equal to 0. And here we have an axisymmetric flow, or if you so that's also equal to 0. And so we end up with this term being 1 over r partial by partial r dvz dr. So let's plug this term here right there. So you get the following equation, and the density cancels out, as you can see here and here. And then we integrate this. So take the r to the left hand side and integrate. So we've taken the r. So when you integrate the partial derivative, that cancels out. You'll end up with the argument of the integral of the partial derivative, and here you have r dr, so you get r squared. dp dz from the assumption is constant, so you get your r squared over 2. And then you get a constant of integration, and here is the argument that we talked about there. Then you integrate again. So first you want to divide by r, so that r goes away. You end up with c1 over r, and one of those r's and the r squared goes away. So when you integrate, that would be r squared. The 1 over r gives you a natural logarithm of r, and this will end up with the argument when you integrate of the derivative. So Vz will end up being as, you'll end up with a parabolic logarithmic equation. And now we have C1 and C2 as our boundary conditions. So we want, as our constants of integration that we want to find through boundary conditions. And let's look at what boundary conditions we have. So this is our pipe. Here you're looking at a cross section of the pipe, and here you're looking at the side view. So if you look at the cross section at r equals 0, well, let's look at r equal capital R. That's at the wall of the pipe. So the flow is going into the page so it's going into the page in this picture. And the fluid element that's in touch with the wall of the pipe will have 0 velocity, so that's your no slip. So Vz at r equal capital R is 0. So, and then if we look at the pipe center line, because our flow is axisymmetric, I would expect that my, if I draw this, if I take a radial cut the velocity distribution here would be symmetric with this guy. And that would require that at this point, the gradient of the velocity, of the axial velocity as a function of relative to r would be equal to 0. That's being axisymmetric. The other way you want to look at it, if you plug in r equals 0, log r equals 0, how does the natural logarithm profile look like? It would actually look like this. If this is 1 here, it goes to infinity at 0. So that's r versus log r. And so at r equals 0, we would get an infinite velocity, which is not physical. So the only solution for that is for C1 to be 0. But then you go back to the first step. C1 will come out to be 0 if you just say that the flow is axisymmetric. So now let's plug. So we found C1, and let's plug in for a Vz of r to get C2. So we end up with C2 from the first boundary condition to be minus r squared. So you plug in r equal to capital R here and here, and we've already found that this was 0, and you get C2 to be, and you take it to the right hand side, that's equal to 0, minus this term, which is this guy, and plug back into our equation C1 and C2, and this would be the form of the equation. So this displayed sooner than it was supposed to, and it looks parabolic. So you have an r squared relationship with the velocity. So the velocity actually drops quadratically from the center line to the walls. And now you want to double check that your solution is correct. So you plug in, you find the derivative at 0, and you find the velocity at the wall, and you should be able to get those boundary conditions exactly. Otherwise, you would have a mistake in your solution. Now, what can we do with this? And this is called a Poisson or pressure-driven flow. And we have seen this in the flow, pressure-driven flow between two flat plates. And it also looked parabolic. So this is the quadratic second order polynomial relationship seems to be, we're seeing that it's repeating every time we have a pressure driven flow when we supply a constant dp/dz. Okay, so now let's go back to our initial question. Now that we have found the velocity distribution, our initial question, if I supply your pressure here and a pressure there, pressure at the inlet that's higher than the outlet, and I have a length of pipe L, and I know what my fluid viscosity and density is, how much mass flow rate am I gonna get in? So now that we have found the velocity profile based on all these assumptions, we can get the mass flow rate and other things too. So one question is, what is the fastest velocity in the pipe? And you'll see if you plug in small r to be 0, that's your maximum velocity. This would be actually your maximum velocity. And if you want the mass flow rate, you just integrate over the area of the pipe, the velocity over the area. So you take a dA here, and the velocity perpendicular to the dA is Vz. So that's your dA, and that's Vz. And if you look at a side view of this dA that we looked at, it looks like this. It's this area. It's this circular slab. And the velocity, as we said, is into the page. Okay. So you find, so this is your volumetric flow rate. and you plug for Vz to be this guy, times 1 minus r square over r square times, so the area that we're talking about is 2 pi r, because all this, the length of this rectangular strip is the circumference is 2 pi r, small r, and the width of this rectangular strip, because once you develop it, open it up, it's going to be a rectangle. So that's dr, 2 pi r dr, that's your area. And you multiply by the Vz, as we have said here, and that's your Vz. You plug it there. So that gives you the volumetric flow rate, the Q, and you divide the Q by the A, you get the average velocity. And if you multiply the Q by the density, you get the mass flow rate. So now this is very familiar with us, to us. And here we get this is your average velocity, and it's related to the pressure gradient, the dimension of the pipe, as well as the viscosity. So how much flow, so if I multiply my average velocity by the area of the pipe and the density of the fluid, I get the mass flow rate. So let's talk about average velocity. It tells you my flow, my speed in the pipe will increase if I increase the delta P, if I make my pipe shorter, and if I make my diameter larger, and if I reduce the velocity, the viscosity. So all those are going to contribute to an increase in flow velocity. The opposite is if you have a longer pipe, less applied pressure, pressure difference between the inlet and outlet, smaller pipe diameter, and higher viscosity, that will all affect your flow velocity to become lower and lower. So you get the point. And one note that we all have to make here is that the relationship between all those 1, 2, 3, 4 between the velocity and those 3 variables is linear, while with the whether it's linear inverse or proportional, but with the radius it's quadratic, it's squared. So the radius is the pretty much the more important parameter in this picture, because a slight change in radius, say 20% increase in radius, will give you a 50% increase in average flow velocity, while a 20% increase in pressure will give you 20% increase in flow velocity. And then we can find the friction between the wall of the pipe and the fluid, and it's the shear stress tau on face R in the Z direction. So it's tau R Z multiplied by the area, and the area that we're looking at it's this area. It's the luminal area. It's different than, so it's 2 pi r times the length of the pipe. So it's this area. Here we see a side view of it, and here we see a front view of that particular area. So that's why it's pi rl. Because you want to imagine, because of the tau r z, the direction is in the z direction. The area that that the flow sees is the inside area of the pipe, not the cross-sectional area of the pipe. That's why it's not pi r squared. So for tau r z, you multiply the viscosity with the strain rate and dvz by dr. So this is vz as a function of r, and differentiate that, and you get a relationship between your friction and the pressure distribution. Let me stop here for a second, and we will discuss this in a little bit more detail, the friction as a function of pressure drop. So we see on one side we have friction, and then you have on the other side the pressure difference between the pipe. So we see there is some equalization of frictional forces or frictional shear with the pressure forces between the inlet and the outlet of the pipe. So let me break the video here to make it short enough to upload, and then we'll continue in the second part of this video. I'll see you in a minute. Thank you.